Okay, so it is time to start, so we can start. Are there any questions before we start? Okay, so I am not hearing any questions, which means that probably there aren't. So I guess so. This might be I think this might be the last topic that will be in the exam. I may teach some topics in the last 1 or 2 lectures that likely won't be part of the midterm exam. So the midterm exam, the last midterm exam should really be on homework 8, 9, 10, 11. And you are turning in homework 9 today. Homework 10 is already posted. Should be due next week this time. And homework 11 should be due a week from that. So, yeah, so I may teach some material in the last couple of classes that likely won't be part of any homework or in any exam. Okay, so I'm going to talk about lattice filter structures and how those are designed from the transfer function and by using the well-established theory long ago based on what is called Schur polynomials. So these polynomials are such that their roots are inside the unit circle, and that is really what we need.
Professor, it's not projecting.
Okay. Okay. Yeah. Thank you. Yeah. So Schur polynomials are polynomials whose roots are inside the unit circle, and that is what we need because in a transfer function, the denominator. The roots of the denominator are the poles of the filter, and the denominator itself should be a Schur polynomial such that its roots are inside the unit circle, and that means the poles of the filter are inside the unit circle, and that means it's stable. If the denominator was not expressed as a Schur polynomial, some of the roots would be outside the unit circle, and that would not be of interest to us because that would be an unstable IIR filter, which would be of interest to us. So we'll talk a little about these polynomials, and then the key part of designing these filters is the process of degree reduction. And so that means if we start with degree n polynomial, then we reduce that to degree n minus 1, then degree n minus 2, degree n minus 3, etc. So start with degree n polynomial and reduce the degree by 1 to degree n minus 1, then by 1 more, degree n minus 2, etc. And all the way go to until constant term. So the last, at the end, we will have a polynomial just one constant term. So in order to design, so we can design many kinds of lattice filters depending on the type of degree reduction process that we use. So in one type of degree reduction process, we can start with, so the book has 3 types of polynomial degree reduction processes, but the 2 of them that we should definitely study, I'm not sure yet about the third one. So the 2 polynomials called phi n and psi n. So this polynomial is an orthonormal polynomial. So there is a difference between orthonormal and orthogonal. So basically when something is orthogonal, the inner product of, okay, so the definition of orthogonality, psi I, psi j is 0, the inner product, and I am not defining what that is. It's a little bit involved, but if I is not equal to j, and psi I is some constant. So that's basically the definition of orthogonality. And if this constant is 1, then that's called orthonormal. So phi inner product is 1, and that because that constant is 1, it's called orthonormal as opposed to orthogonal. So we can derive different kinds of lattice filters depending on the degree reduction process that we follow. And in one process, we start with this phi n reduced to phi n minus 1, phi n minus 2, and so on. In the other degree reduction process, we can start with psi n and then reduce that by 1 and psi n minus 1 and minus 2, etc. So that's kind of one aspect that we need to understand, and we'll talk about that. The whole lecture is it's all about reducing the degree and deriving the structures for lattice IIR. I should say IIR. We are also interested in the FIR. So FIR is also of interest, but the real interest was with respect to IIR, and there are certain properties in lattice digital filters that are attractive for IIR filter implementations. In particular, all the coefficients are bounded between -1 to 1, and that's of great interest. So the number of bits that we have to allocate to those coefficients is the same throughout all the stages. The other attractive property is, at least in the orthonormal case, it's already in a scaled form so that the filter is orthonormal. So okay, so let me so basically when the filter is orthonormal, that means, so think about again each state variable. If you think about the covariance matrix and that equation that we had, this so-called Lyapunov equation, which was K is equal to BB transpose plus A times K times, so basically the equation that we are solving, or trying to expand here, K is equal to BB transpose plus A times K times A transpose, right? So if you take A outside the left bracket and A transpose outside right bracket, what's left inside is K, and if the filter is orthonormal, then that K becomes an identity matrix. That means the inner product of each state or the covariance of each state with itself is going to be 1. And for an orthonormal digital filter, we can then say that it has to satisfy BB transpose plus A transpose should be identity matrix for orthonormal filters. Okay, so that's the main difference. The states are always orthogonal because the inner product of one state with respect to another state is 0. That's the condition for orthogonality. Orthonormality means the inner product of itself, of the state with respect to itself, is going to be 1 when it is orthonormal, and some other constant when it is orthogonal. Okay, so what is this process of degree reduction and the lattice structures? So the way the IIR lattice, so think about what an IIR lattice looks like. So we have a filter Okay, so think about, So degree n, if the filter is of degree n, then we have n stages, okay, n stages. And each of these stages is described by something called a reflection coefficient, K coefficient, also called a reflection coefficient. So in the case of IIR lattice, so the coefficients are Kn, Kn minus 1, Kn minus 2, all the way through Kn. So that's these are ultimately, these will be the coefficients that describe the denominator. Okay, so if this is, if I used the orthonormality, that would be called the normalized lattice. For example, phi n. So if this was phi n, so the degree reduction process will make sure that the variables associated with these will be Pn minus 1, etc. And what is the interconnection going from right to left is what is called the reverse polynomials, and we'll talk about that and we will define these, what these are. So these are called the reverse polynomials, the star polynomials, and we will talk about that, we'll define what these are. And so the variable, the polynomials, think about these as polynomials associated with these are going to be the reverse polynomials going back. So ultimately this is just a constant term, okay. So its reverse polynomial is itself, so we just connect the top output back to the bottom input so that it keeps propagating. Okay, so the transfer function, if this was the input and this was the output, so let's call this out 1. If this was the out 1, so the transfer function from input to out 1 will simply be that constant, maybe. So in case of phi, that constant will be, I believe that will be 1. But let's call it phi 0 for now, should be 1. But yeah, so phi 0 by phi n, and this would be called, this is a constant, and that's called an all-pole filter. All-pole filter means the filter has no zeros. So the numerator is simply a constant term. So an all-pole means no zeros of the filter. And how do we get zeros? We can incorporate zeros by having the numerator polynomial that can be expanded using either the top polynomials or the bottom polynomials, and that's how we will implement the transfer function with poles and zeros. But let me just write down, if this was the output, so the transfer function from input to output 2 would be phi n star by phi n, and that reverse polynomial, I'll talk about that in a minute. And this would be what is called an all-pass filter, and I won't get into a lot of details, but essentially the poles and zeros are in complex conjugate pairs. Excuse me, are in reciprocal pairs. Okay, so if a pole is at, I think it's a reciprocal conjugate pairs. So that means a pole at A implies a 0 at 1 over A conjugate. Okay. So that's the property of all pass filters. That means the numerator polynomial is the reverse of the denominator polynomial. So again, we do talk a lot about these kinds of things in an undergrad DSP class, but I don't really intend to talk more about that. We are interested in understanding structures and something more that we will get into, how to pipeline the lattice structures using the scattered lookup form. Okay, so let me just briefly mention how to implement pole zero filters, and then we'll start talking about the degree reduction process. So if we have a filter like that, then to implement numerator by denominator, so I can describe the numerator polynomial as a sum constant Ci. So this is phi n minus 1 up to phi 0, phi iz, I equal to 0 to n. Okay, so that's kind of, so that means I can multiply some constants to these polynomials here, and then I can add them either from right to left or left to right. It doesn't really matter because add operation is associative. So if this is the output now, so that would be transfer function from the input to output. So this would be pole zero filter. I could expand the numerator polynomial from the bottom, the so-called reverse also. I could do that. That's possible to do that, and that is perfectly fine. There is nothing wrong with that, and that's another way. And all of these things could be added from right to left or from left to right, these products. It doesn't matter. So that's how we can realize pole zero filters. The pole zero filters still make use of the same reflection coefficients. Okay, so what about FIR lattice? In the case of FIR, these are based on, instead of degree reduction, these are based on a degree well, okay, still I could say still degree reduction, but so these are FIR. So if you take any cut set here, there is data moving to the right in the top path and to the left in the bottom path. The FIR is completely feed forward. That means data are moving in one direction. So if I take so here we start with K1, K2 and go up to Kn at the end, and because this polynomial is just a constant when we start, then all the data go forward in both top and bottom paths, and that's called the FIR lattice. And as you can see, there is no feedback loop because data are all moving forward. Okay, so as opposed to the IIR lattice where some data are going forward and some data are going backward. So every cut set will be a feedback cut set here. Okay, so let's start with what is this degree reduction process, and to get into degree reduction process, we need to talk about the definition of reverse polynomials. So let's say that I have a polynomial a of z, some polynomial is 2 plus 3 let's say 2z to the power 4 plus 3z cube plus 4z squared plus 5z plus 6, for example. Okay, then we say the reverse polynomial of that is, if you think about these coefficients 2, 3, 4, 5, 6, and then you reverse that, that becomes 6, 5, 4, 3, 2, and then the reverse polynomial will be the same polynomial with reversed coefficients. So 6, 5, 4, 3, and 2. So that's the reverse polynomial. Okay, so a formal way of defining the reverse polynomial, a star z is equal to z to the power n a1 by z. So that is the formal definition, where n is the degree. In this example, degree is 4. So if I take z to power 4, a1 over z, and that would be z to power 4 times, if I replace z by 1 over z, so 2 z to power minus 4 plus 3 z to power minus 3, replace z by z to power minus 1 plus 4 z to power minus 2 plus 5 z to power minus 1 plus 6, and so that is 2 plus 3z plus 4z squared plus 5z plus 6. And if you read that from right to left, it's the same expression. 6, something went wrong, 4 minus 1, 3, and then z to power 4. Okay, so these are the same expressions. So that is the formal definition of defining a reverse polynomial. You replace z by 1 over z in the polynomial and multiply by z to power n. So while taking the reverse, one has to be careful because it's easy to make a mistake, particularly if some of the coefficients are 0. So for example, if a z is equal to 2z to power 4 plus 5z plus 6, okay, then what will be its reverse polynomial? So one may be tempted to think it will be 6z to power 4 plus 5z plus 2. Okay, but that's not the case. So the way to think about that, if you want to use the reversal of the coefficients, you have to write the coefficients as 2, 0z cubed, 0z squared, 5z and 6, and you reverse that, we get 6, 5, 0, 0, 2. So this will be 6 z to power 4 plus 5 z cubed plus z squared 0, z 0 plus 2. So that's why we need to be careful. If just manually writing down the coefficients in reverse order, and if some of the coefficients are 0, then we need to be careful in how we reverse. But this is always true. So if I took that as z to power 4 times, replace z by z to power minus 1, 2z to power minus 4 plus 5z to power minus 1 plus 6, and then you can see that z to power 4 minus 1 is 5z cubed. So either way is okay. If you are following manual method of reversing coefficients, make sure to include all the terms, even if some of the terms are absent. We need to include those coefficients to be zeros. Okay, so that's the definition of reverse polynomial, which means the coefficients are present in reversed order. Okay, so now let's talk about how the degree reduction process can begin using the original polynomial and the reverse polynomial. Okay, so let's start with this orthonormal polynomial that we were talking about, and then we'll talk about the orthogonal polynomial. So if I start with the Schur polynomial Pnz, so this is the orthonormal polynomial and let's say that this one is some constant phi n times z to power n plus phi n minus 1 z to power n minus 1 plus phi 1 z plus phi 0. Okay. Then if we reverse that phi n star, then this will be phi 0 plus phi 1 plus phi n minus 1 plus phi n. So that is going to be the reverse polynomials. So take these coefficients and reverse them, and then that's the reversed order. So how can I reduce the degree by 1? So the process of reducing the degree by 1, so if you look at the two polynomials and I want to reduce the degree by 1, so think about okay, let's just make some observation. So the first observation is, if I'm going to reduce the degree by 1, let's try to multiply this by phi n. Okay, so this is phi n squared, phi n, phi n, phi n. And multiply this by phi 0 okay, and then subtract them. Okay, if you subtract, this term cancels out. So that's the reason I'm trying to eliminate. I'm trying to eliminate that constant term. So once the constant term is eliminated, so this quantity minus that quantity, then there is this z here. There's no constant term now, but if I multiply by z to power minus 1, the first term will be some quantity, that quantity phi n squared minus phi 0 squared times z to power n minus 1, and the last term now multiplying this will be phi n phi 1 minus phi 0 phi n minus 1. That's it, because the z and z inverse will cancel out, and that will have degree n minus 1. So that's really the essence of reducing degree. So that's the essence of reducing degree. Degree can be reduced by multiplying phi n to this quantity. So if I, from that observation, I can say, okay, so phi n, cap phi n minus phi 0, phi n star, the reverse polynomial, is equal to z to power so let's just write down what we have now is phi n squared minus phi 0 squared times z to power n plus phi n minus 1 minus phi 0 phi 1 and the last term phi n phi 1 minus phi 0 phi n minus 1 okay times z. Okay, so now there is times z here. Okay, so now if I take phi n outside, so I can write this as phi n outside the bracket, and then this phi 0 by phi n. So So phi n is taken outside a bracket, and we'll see in a minute why we do that. And the reason we are doing that is because the k coefficients we were talking about, all these k coefficients, these are expressed. So this quantity here is the Kn, the nth deflection coefficient. So if I take phi n outside, then this becomes phi n minus Kn phi n star. And from the right side, if I take phi n squared outside a bracket, and let's see what we are left with. Okay, if I take phi n squared outside a bracket, then this will be divided by phi n squared. Okay, so we divide phi n squared everywhere. Okay, then this phi n cancels out on the right side with that square. Okay, so if we cancel that term out, so we have now phi n. Okay, so now we can write down this is equal to z taken outside a bracket, this whole z taken outside a bracket, phi n taken outside a bracket, times, so this quantity is 1 minus Kn squared times z to power n minus 1. Okay, plus phi n cancels out with 1 phi n, so we are left with phi n minus 1 by phi n minus phi 0 by phi n is Kn, that's Kn times phi 1 by phi n. It doesn't probably matter all that much. Z to power minus 2 plus, it doesn't probably again matter, some constant term, because this z has been taken outside a bracket, and that's some constant term. Okay, so then if I multiply z to power minus 1 to both sides, so I can essentially take this to the left side. Okay, then that so this you can see that whole right hand side is of degree n minus 1. And then the last step, so how we define, this is where the degree reduction process between different kinds of polynomials can change. So in the phi polynomial, we divide the both sides by square root of 1 minus Kn squared, square root of that. Whereas when we reduce the degree of this so-called psi n, then we just divide by 1 minus Kn squared. So that's the difference between how we reduce the degree from depending on different constants. So suffice it to say that the degree reduction process for the phi polynomial or the orthonormal polynomial is defined as phi n minus 1 z is equal to what we had here, divided by square root of 1 minus Kn squared. So that is the degree reduction process. For the psi polynomial, everything is the same except that the square root goes away in the denominator. So this 1 minus Kn squared quantity is divided on both sides. Okay, so that's any questions so far? Questions about reverse polynomial or how we are defining this degree reduction process, and at least you should be convinced that by going through that process the degree is indeed reduced by 1 because we removed the constant term we multiplied by z to power minus 1. So that thing here became cancelled out. So it's just a constant term at the end. The first term becomes z to power n minus 1. Okay, so that is the degree reduction process. So maybe I can work out some numbers, but maybe instead I can show you what the results look like without working through these numerical examples. Okay, so if we look at this example 12.2.1, so this is a denominator of a third order IIR filter with this quantity 345.1 Z cube and so on. Okay, and the reason I'm starting with that is because we'll ultimately use that to design lattice digital filters. And if you are thinking about, okay, how did I get that kind of a strange looking number, and that really came out of a Butterworth filter. So essentially the reason I'm starting with that example is because that particular filter came out of a third order Butterworth filter from the MATLAB command. And as you can recall, the Butterworth filters will have numerators of this 1 plus z to power something. If it is degree 3, then it will be degree 3. And then we get that denominator. And that's really how I'm starting with that denominator, which has to be a Schur polynomial because it's a stable filter. Okay. And I won't go through these processes here of reducing these degrees. But if we did start with that denominator as phi3 and go through that process of reducing phi n minus 1 is equal to z to power minus 1 times phi n minus kn phi n star by square root of that. And you can convince yourself, and again by maybe working out the homework problems, is that the phi 2 will be that, phi 1 will be that, phi 0 will be that. And the sum of the observations of the Schur polynomial, the coefficient of the highest power of z is larger than the constant term. So if you look at the constant term, these will be always more than the constant term. Okay. Why is that a property? I mean, the reason, so if I took this 345.1 outside a bracket, these numbers should be less than 1, right? Why is that? So if the coefficient of the highest power of z was normalized to 1, why should this be 1? Because in a polynomial, the first coefficient is 1, the next coefficient is the sum of all the roots, r1 plus r2 plus r3, etc. The next one is sum of two roots taken at a time, r1 r2 plus r1 r3 plus r2 r3. If there were 6 poles, then this would be sum of 6 choose 2, 15 quantities. The last, however, is the product of all the roots. And if all the roots are inside a unit circle, then their product will be less than 1. That's the reason why this term is always less than the coefficient of the highest degree term. Okay, so before we talk about lattice filters, it is useful to talk about how to expand the numerator polynomial. So the numerator polynomial that I was talking about, n of z. And well, I could delay this part. I could certainly talk about, well, okay, let's just delay. Let's get back to that part, expanding numerator, before let's talk about the degree reduction processes first, and then talk about the expanding the numerator. So we'll talk about that a little later. Okay, so so this is when we use this degree reduction process and we get a lattice structure, that's really called a normalized lattice filter. The other polynomial psi n minus 1 z, the starting point of phi or psi is the same. And then if I just write down by 1 minus kn squared, and this is the orthogonal polynomial. And if we design a lattice filter using that degree reduction process, that particular lattice structure is simply called the basic lattice filter, or sometimes called the Gray-Merkel lattice filter, named after the people who proposed this filter in the beginning. Okay, so we are done with first part. We are done with understanding what is degree reduction and how that happens. So the next part that we want to understand is how do we decode this black box. So what's inside that box that takes one input from the left top, one input from the bottom right, and then generates two outputs, the top right and bottom left. So some of you may realize this is kind of a hybrid structure as opposed to data going forward or all going backward. Some data, two signals are going into the box from left and right, and two signals are being generated from the box, one to the right, one to the left. So we will get different description of that box depending on if I use that degree reduction or this degree reduction. So the particular degree reduction will lead to a different kind of stage, so-called lattice stage. Okay, so let me begin with this basic lattice filter, because that's the first structure that existed. And by the way, it may not be obvious, but if we start with the basic lattice filter and apply a transformation matrix, then we can reduce that to a normalized lattice filter by applying the scaling and round of noise matrix type of idea. The K, if you compute the K matrix and take the diagonal values Kii, take the square root of those and construct the transformation matrix T, and then apply that to the basic lattice, then you go back to that normalized lattice. So we won't spend a lot more time, but these are all related anyway. So yes, so there is the theory of transformation, linear transformation. So both of these structures are related to each other by a linear transformation. Okay, so let's start with the derivation of basic lattice filter. Okay. So we need to get two equations. If you look at if I think about let's say this is Kn, and start with psi n star, psi n minus 1, psi n minus 1 star. So I need to compute, so I need two equations. So I need psi n minus 1 is the sum function of the two inputs, and psi n star is some other function of the same two inputs. So that's kind of what to deconstruct or to obtain what's inside that box. I need two equations for these two outputs. We need two outputs and two equations to compute those two outputs. I need to express psi n minus 1, the degree reduced polynomial, and the reverse polynomial of psi n with respect to these two quantities that are input to the structure, to that stage, the nth stage. And once I get the box of the nth stage, just replace Kn by Kn minus 1, Kn minus 2, then you get what's inside the box, each box. Okay. By the way, before I go further, it's probably useful to just mention. It's useful to mention that. So we were talking about what is Kn. Kn is phi 0 by phi n. So that 183 minus 183.6 by 345.1. And if we reduce the degree, then K2 is going to be 271.5 by 292.2. That's K2. K1 is going to be this constant by the highest power coefficient, minus 105 by 107. Okay, so K3, K2, K1. So once I reduce the degree, each time I can get the K coefficients by taking the ratio of the constant term to the coefficient of the highest degree term. And again, because the constant terms are less than that, all the K coefficients will be less than 1 in magnitude. Some could be positive, some could be negative. For example, here that's negative, that's negative. But at least it's good to know how we get those K coefficients. K coefficients become available as we keep going through the degree reduction process. Okay, so let's start with how to get these two different equations. So psi n, so let me take the reverse polynomial of psi n minus 1, psi n minus 1 star z. Okay, by definition, this is z to power n minus 1, psi n minus 1, 1 over z. Okay, that's the definition. And I can write that as z to power n minus 1. So replace z, wherever there is z, replace by 1 over z. Okay, so this z to power minus 1 becomes z. Okay, z replaced by z inverse. Psi n 1 over z minus kn psi n star 1 over z. Okay, z replaced by 1 over z divided by 1 minus kn squared. Okay, so what is the right hand side? So the right hand side, so psi n star, so this quantity psi n star is z to power n psi n 1 over z. Okay, so now what I need to do is replace z. So to compute psi n star 1 over z, replace z by 1 over z on this expression. So that becomes z to power minus n, z replaced by z to power minus 1, psi n 1 over z becomes z. Okay, so that's that reverse polynomial. And then z to power n minus 1 times z is z to power n. So this whole thing is z to power n. Okay, so what I get then is z to power n psi n 1 over z. So this times that, and this z to power n cancelled out with z to power minus n, psi n z by 1 minus k n squared. Okay, all right. And what is this quantity? This quantity is psi n star. So that is equal to, I forgot it, or kn. So that is equal to psi n z, that's the definition of, psi n star z, that's the definition of reverse polynomial, minus kn psi n z by 1 minus kn squared. Okay, so now we have been able to describe the reverse polynomial psi n minus 1 star in that form. So I can then cross multiply this to the left side, take this quantity to the left side, then I get psi n star z is equal to 1 minus kn squared times psi n minus 1 star z plus kn psi n z. Okay, so take this to the left side, take this quantity to the left side, so this quantity is equal to 1 minus kn squared times that quantity plus this quantity. Okay, so this then can be written as, so there is a little bit of arithmetic, but at the end we will get the two equations we are looking for, and it takes a little time to get to those equations. So psi n star can be written as psi n minus 1 star z. So that's the first term. Now we have two terms here left, minus kn squared times that plus kn times that. So plus kn taken outside a bracket, psi n, that's the last term, minus, from this minus kn squared, we took one kn out, the other kn, psi n minus 1 star z. Okay. Okay, so this is definitely good. We have made some progress, but it's not really complete progress, because what I am looking for is an equation that expresses psi n star as a function of psi n and psi n minus 1 star. So and the second psi n and psi n minus 1 star. Okay, so there is a little bit of arithmetic that we can do. If I go back to the original degree reduction process. Okay, so the degree reduction process psi n minus 1 is equal to z to power minus 1 psi n minus kn psi n star divided by 1 minus kn squared, and then if I replace this here, so replace that quantity, then this is z to power minus 1 psi n minus kn psi n minus 1 star minus kn times plus kn is minus kn squared minus kn times minus kn squared plus kn cube divided by 1 minus kn squared. Okay, so so from this term and that term, we can take 1 minus kn squared, that psi n taken outside a bracket, 1 minus kn squared, that cancels out with the bottom 1 minus kn squared. From this term and that term, I take minus kn times psi n minus 1 star outside, then that becomes 1 minus kn squared. 1 minus kn squared ultimately cancels out in the denominator, and we are left with z to power n times psi n minus kn psi n minus 1 star. Okay, so that's kind of one equation that I need. I skipped a step, but that's basically 1 minus kn squared is a factor from this minus that. 1 minus kn squared is a factor from this plus that, take this minus kn psi n minus 1 star out. 1 minus kn squared, that's cancelled out. So that is one of the equations. That's one of the equations that says that I can construct. So if you look at the basic lattice stage, so to construct psi n minus 1 z, that output here is psi n minus kn, so psi n minus 1 star coming from right, multiply by minus kn, and that becomes z psi n and multiply by z inverse. So psi n minus 1 star multiply by minus kn, that multiplied by z to power minus 1, and that is psi n minus 1. Okay, so that's the first output, and so basically you can think of this intermediate term as a z times psi n minus 1. Okay. So that's that output. So I still need to compute the output for the reverse polynomial coming out here, psi n minus psi n star. Okay, so how do I get psi n star? Okay, so here is how we get that. So psi n star is equal to psi n minus 1 star plus kn times, now what is this quantity? That quantity is here, psi n minus kn psi n minus 1 star. So let's just bring this to the other side. Okay, so that's that quantity. So that's really, so this is equation 1 and that's equation 2. Those are the two equations I need to define that black box, and we are done. So it says that take this z psi n minus 1, that intermediate point, multiply by kn, add to psi n minus 1 star, and that is the reverse polynomial. So that is the basic stage. So that's there. If this is n stage basic lattice, there will be n such stages, one after another. All we need to do is we reduce the degree, replace kn by kn minus 1, kn minus 2, etc. And so basically keep repeating these stages. At the very end, the polynomial psi 0 will be a constant, and we just connect that back to itself because the constant term. That's how we complete that whole IIR lattice. Okay, so so that completes the IIR basic lattice. I think this is probably a good time to just go back to that expansion of the numerator polynomial. Okay, so I won't go through these numerical examples, but so going back to that third order Butterworth lattice coming out of a MATLAB command, so we get this denominator, put that equal to psi 3, psi 2, psi 1, psi 0. This coefficient you can see at the top coefficient, it's remained the same. K3 minus 183 by 345, K2 320 by 345, and K1 minus 336 by 345. So that so the whole if you connect those things, that lattice filter, the all pole lattice, all pole. If this was the input, this was the output right here. Excuse me. So the all pole lattice transfer function would be what? Would be the polynomial here, and believe it or not, that polynomial there is psi 0, which is 345.1. So the all pole lattice that we can get would be 345.1 divided by that whole denominator. So that would be the transfer function if I took the output from here, okay, and the input is here. If the input is here, output is here, the all pass, the poles and the zero, so there is a numerator. So the numerator is simply the reverse polynomial of the denominator, and that transfer function is going to be, this is the denominator is same for the all pass, the numerator is going to be minus 183.6 z cube plus 665 z squared minus 819 z plus 345.1. So that would be the numerator, the reverse polynomial of that denominator, and that would be all pass. But if I want to compute 1 plus z whole cube as the numerator, z cube plus 3z squared plus 3z plus 1, so to expand that, so okay, so we want to expand the numerator polynomial in terms of psi 3, psi 2, psi 1, psi 0 in this example. And how we can do that is by equating the coefficients. So n of z can be written as c3 times psi 3 plus c2 times psi 2 plus c1 times psi 1 plus c0 times psi 0. And the so n of z, which is z cube plus 3z squared plus 3z plus 1, that is the 1 plus z whole cube. And the psi 3 is, so this one here is 345.1 z cube minus 819.3 z squared plus 665.8 z minus 183.6. Okay, so what is C3? C3, equate the coefficient of z cube on both sides. C3 times 345.1 is equal to 1. Equate coefficient of z cube on both sides. So C3 is 1 by 345.1, which is 0.0029. Okay, so once we get that, what is the process? What is the process to get C2? So the first step, of course, is to get C3. So that's the first step. So once C3 is done, then what's the next step? Reduce the degree by 1. So NZ minus C3 psi 3. Okay, so compute, so take this to the left side. So NZ was this quantity. Z cube will be cancelled out. Z cube minus, that's coefficient 1, minus C3, which is 1 by this 345, times 345, that's cancelled out. So Z cube will be cancelled out. And this is going to be 3Z squared minus minus what? So 819 0.3. Okay, so not 3. So 8 minus 819.3. So if I multiply by 345.1, so NZ minus, so C3 is multiplied by that Z squared, okay, plus some Z and so on. Okay, so there will be other terms. That's plus. Okay, I need to look at what psi 2 is. Psi 2 is also 345.1 Z squared minus 648. Okay, so this quantity here, so C2, psi 2, so this one here is 345.1 Z squared and others. I'm not writing down the other quantities. So now, so the coefficient of Z squared is going to be this quantity plus C2 times 345.1. Okay. Okay, so let's take a look at if I get the expansion coefficients or not. So once we compute N2, so if we call this N3, then compute N2, which is N3 minus that. Okay, and if you do that, this becomes 5.37 Z squared plus 1.07 Z plus 1.53, and this is equal to C2 times psi 2 plus C1 psi 1 plus C0 psi 0. And okay, so I'm going to skip this part because let's just go back to see what is in the book. I think the example that expands is with respect to phi polynomial, not psi polynomial. But let's just take a look here. Yeah, so those numbers are different because the example in the book, the process is same, but the answers are a little different. But you can do that yourself. You can do that. So you will compute the C2, C1, C0, and as the book indicates, those are obtained here. So let me just say why it is a little different. So if we go through the expansion example in the book, this is using phi polynomials, not psi polynomials. And if we did that, then the C2 is different from, so for example, C2 is 0.0184. Using the psi polynomial in the lattice, that's 0.0156. So that's different, which is what we would expect. So, but still the process is still the same. So each time each time reduce the degree of the numerator and keep repeating that process. And if you finally put all of these together, so this was psi 3 times C3 degree reduced, psi 2 times C2, psi 1 times C1 plus psi 0 times C0, and you add them up, that's the output, which is 1 plus Z whole cube. Okay, so that's really how we compute the pole zero filter. There is a little more in the book, and I may not want to I can just mention, it is possible to take that numerator from the bottom polynomials instead of the top polynomials. So these psi 3, psi 2, psi 1, psi 0 form a basis set, form an orthogonal basis set. and if we expand them from the bottom polynomials, then what is proven, I guess it takes a little time to prove, and certainly not as trivial as one would think, but as proven in a couple of equations here, and I'm not going to prove it now. But these coefficients 0.0029 up to 0.0215 happen to be same coefficients if taken from the bottom. So, okay, so using the reverse polynomials, so now these are the psi and psi 3 star, psi 2 star, psi 1 star, psi 0 star. Okay, so so we can add these from left to right, right to left, it doesn't matter. We can expand the numerator with respect to the reverse polynomials or with respect to the degree reduced original polynomials. So, but that's the basic essence of the lattice filter. So I'm not going to start the normalized lattice today because we just have a couple of minutes left, but it's probably okay to point out some things. Okay, so let me see what I can point out. So for the IIR, so if you think about the let me just explain little more. I have to explain little more. So it is not that these coefficients remain the same. It's not that. It's okay. There is a fundamental difference. It's not that we took this and expanded the numerator from these points. We didn't do that. Okay. The first thing to do is to do a retiming. So if you think about retiming, push this delay to the bottom. So take these cut sets. So what we have done is we have pushed the delays on the top to expand with respect to bottom. We have pushed those delays to the bottom. So the top delays have come to bottom and then we are able to expand. Okay, there is a lot of theory and I really don't want to go into that theory. And it turns out the polynomials psi 3, psi 2, psi 1, psi 0 form an orthogonal basis set. What is not true is the reverse polynomials do not form an orthogonal basis set. So the psi 3 star, psi 2 star, psi 1 star, psi 0 star do not form an orthogonal basis set. However, the psi n star, z times psi n minus 1 star, z squared times psi n minus 2 star, z to power n times psi 0 star. So these do indeed form an orthogonal basis set. And because of that, by pushing the delay to the bottom, okay, we are able to convert these polynomials on the bottom from psi 3, psi 2, psi 1, psi 0 to psi n star, z psi n minus 1 star, etc. So if you look at the when expanding with respect to the bottom, the delays from top have been pushed to the bottom, and the polynomials now associated with top and bottom, psi n star, z times psi n minus 1, because that's ultimately what I had. So this was z times psi n minus 1. We push this down, the next one becomes z squared psi n minus 2, z squared psi n minus 2 star at the very end. All the delays are in the bottom path, z to power n psi 0, z to power n psi 0 star. Okay, so that's kind of something to keep in mind. Before I start, again, we won't do this today, but before I start the normalized lattice, next class, I will spend a little time how we can have the FIR lattice from the two equations that we derived, 1 and 2, and then the way the FIR lattice, the forward lattice starts, we start with a z to power n psi 0 star, and then keep reducing degree by 1, z to power n minus 1 psi 1, z to power n minus 1 psi 1 star, and the delay is on the bottom path here. So we'll derive that box, and then we'll talk about the normalized lattice, which looks slightly different. If you look at not that diagram, we will derive the normalized lattice where the box looks like this. So all this, there are 4 multipliers per stage as opposed to 2 multipliers per stage. Okay, I will stop now, and we will continue this next class.
Back to the forward with idea.
I appreciate this though. I can't remember class it was last semester and like briefly talked about these. I had no idea how they work. Appreciating like,
You did take 45, 41 last semester.
yeah.
Very cool. That's